It's the history of challenge and shaping the path of our world. Faster, safer, and more convenient. It's the history of further advancing our cutting-edge technology. The time has come. With aerodynamic design and application of magnetic liberty technology, as well as the ability to accelerate up to 311 miles per hour. We introduce the Maglev train.
The introduction. Magnetic levitation, commonly known as maglev, represent a revolutionary paradigm shift in the field of transportation. Unlike traditional trains that rely on wheels and tracks, maglev trains use advanced magnetic technology to hover gracefully over their guideways, eliminating friction and promising unparalleled speeds. Next, we move to the importance of magnetic levitations, which is maglev trains. So the first one, we have unprecedented speed. The maglev trains are known for their ability to reach incredibly high speeds, which is 603 km per hour, far faster than conventional rail systems. The absence of frictions allow for smoother travels, and maglev technology opens the door to rapid transit, reducing travel times between cities and regions. The second one, efficiency and low maintenance. The frictionless nature of maglev technology result in reduced wear and tear on both trains and infrastructure. This not only increases operational efficiency but also reduces maintenance costs, providing a more sustainable and cost-effective transportation solutions. And the last one, environmental sustainability. Maglev trains offer an environmentally friendly alternative to traditional modes of transportation. The absence of direct contact with the track minimizes noise pollution, and the potential to use clean energy sources contributes to a greener and more sustainable transportation systems. So let's move to relevant electricity and magnetism in the maglev trains. First one, electromagnetic suspension or EMS. Maglev trains use an electromagnetic system to achieve levitation. Electromagnets are integrated into trains and guideways. When an electric current flows through an electromagnet, it creates a magnetic field, and then the push or pull between the train magnetic field and the guideway causes the train to hover on the track without any physical contact. The second one, propulsion with an electromagnetic coil. Maglev trains use electromagnetic coil for propulsion. As the train moves forward, the magnetic field produced by the coils interact with each other, pushing the train along the guideway. This electromagnetic coil control enables precise acceleration, deceleration, and braking of maglev trains without the need for traditional wheels and brakes. And the last one, superconductivity for efficiency. Superconducting materials, which exhibit zero electrical resistance at certain temperatures, play an important role in maglev technology. Superconductors allow the creation of a strong and continuous magnetic field without the energy loss associated with resistance, contributing to the overall efficiency of maglev trains.
Now let me explain about maglev train details. First, magnetic lift uses powerful magnets to lift the train a few inches above the track, eliminating frictions and enabling high-speed travel. Propulsions. Maglev train propulsion is achieved through the interactions of magnetic fields. Electromagnetic coils at the bottom of the train are pushed and pulled by magnets on the guideway propelling the train forwards. Speed. Maglev trains are known for their high speed capabilities. Some experimental Maglev trains have reached speed in excess of 600 km per hour, significantly faster than traditional rail system. Efficiency. There is no physical contact between the train and the track. There is minimal frictions. This results in increased energy efficiencies and reduced wear and tear on the system. Next, noise reductions. Minimal noise production compared to traditional trains, as there are no wheels scraping on the track. This makes Maglev train ideal for urban environments where noise pollution is a concurrence. Safety. Absence of physical contacts between train and guideway reduce the risk of accident caused by slipping off friction-related issue. Environmentally impacts. Maglev trains are considered environmentally friendly due to their energy efficiency and low emissions. The reduction of noise pollution also contributes to a positive environmental profile. The most notable example of Maglev train implementations in Japan is a Q Shinkansen Maglev line, also known as SCMAGLEV, superconducting Maglev. This project was developed by the Central Japan Railway Company, JR Central, and was invented to connect Tokyo and Osaka, two major cities in Japan. SCMAGLEV strength is used superconducting magnets and magnetic levitation technology for propulsion and levitation, enabling high-speed travel. It showed record-breaking speeds during the test run in 2015. The L0 series SG's Maglev reached a speed of 603 km per hour in a test run conducted on Yamanashi Maglev test line. Conduction work on the Chu Shinkansen Maglev line began in 2014. The project involved an intensive tunnel through the Japanese Alps and other challenging terrains.
Before this, we talked about many technical aspects of physics in the maglev train. So now, it's time for me to explain what are the advantages of this fastest train in the world. Number one is the high level of safety. Synchronous propulsion makes the collision between maglev unimaginable. What is synchronous propulsion? First, imagine that if two trains were placed simultaneously in the same guideway segment, they would be forced by the motor in the guideway to travel at the same speed in the same direction. Instead, maglev are using the dedicated guideway without intersection. The infrastructure is designed to withstand a collision with smaller objects, and because of the levitation, they glide above most of them. In addition, maglev has a perfect safety record with millions of kilometers of service history. Number two is no derailment. Magnetic levitation technology eliminates the safety risk of operating conventional rail transportation system. Trans-rapid vehicle will wrap around the guideway beam, which indirectly increases the risk of accident to occur. But the maglev train levitates between the guideways, making a derailment virtually impossible. Number three is the high speed. Maglev are famous for their incredible speed. They are fast or faster than most propeller aircraft. Conventional rail is not far off in the testing environment. The LGV, as French TGV train, has a record speed of 574.8 km per hour, which is not even 30 km per hour slower than the maglev record set by the LO series SCMAGLEV of 603 km per hour. The difference is safe commercial operation. The LO series has an approved commercial top speed of 505 km per hour, whereas the current fastest operating conventional train, the CRH380 series in China, is topping out at 350 km per hour only. Number 4 is the energy efficient. With its non-contact levitation and propulsion technology, highly efficient linear motor, and low aerodynamic resistance, the maglev system energy consumption is very economical compared to other transportation modes. There is no energy loss due to friction. Therefore, the faster the train, the larger the difference between maglev and conventional rail technology. The energy efficiency of an ICE-3 train is on par with Transrapid at a speed of 300 km per hour. However, at 350 km per hour, the maglev is 6% more efficient, and the gap gets larger the faster they go. Future systems are promising even better result. Japanese SCMAGLEV claims to have 30% lower energy consumption than the Transrapid maglev train used in Shanghai. And the last one is the climbing rate and maneuverability. The least known fact about maglev technology is its ability to climb step cliff. This enables the planning of maglev infrastructure in more demanding environment with hills and valleys. On top of this, maglev train can take higher turn than regular rail. For example, a normal railway angle of inclination is 4% maximum gradient, but the maglev train gets a maximum inclination of 10% maximum gradient. Everything has its advantage and disadvantages. So now we will together see what the challenges are in relation to the construction and use of this maglev train. One is lack of support from federal and local government. The main challenge were a lack of commitment and support from the federal and local government to finance the massive infrastructure capital investment for building the maglev railways, which cannot be integrated with the traditional railway lines that are already in use. The maglev rail system requires the use of rare earth elements like scandium, yttrium, and 50 lanthanide. This is clearly going to cost a lot and require a lot of funds to be given if you want to realize this mega project. Number two is the cost justification. Return on investment, private and agricultural land restriction, political gridlock and priorities, environment and socio-economic protests, cost-sharing issue between megacity along the rail lines, high-quality standard, requirement and regulation issue in the country, safety and security risks, and legal liabilities. These are some justification why this is difficult to realize in a country that with a small economy. Other than that, the adequacy of the project infrastructure construction fund required for the maglev train and the supply chain availability for the rare earth element were not properly assessed, which was also a factor in the failure of this project. Plus, maglev guide paths are more costly than conventional steel railway tracks. Because the magnetic coils and the material used in the setup are very costly, the maglev rail line should not have sharp curvatures and geometric turns along the traffic roads, which can shorten the path in some way by using shortcut. But this maglev train requires an all-new setup right from scratch. It is hard to do and very costly. Number three is the timelines of the technology and economic life cycle of the railway infrastructure. Most of the traditional railway infrastructure in the US, Europe, and Asia was built around the 1950s, and the train transportation system were privatized before they evolved to the extent necessary to adequately meet the growing need of passengers. The computer technology to support the required automation control for maglev train were in their early stage. Although the maglev is quiet and no engine is required, noise caused by air disturbance still occur. They are feasible only in urban area because of private agricultural land restriction in the most country. And the last one is the EMS system. The second widely used technology behind maglev train is electromagnetic suspension, known as EMS. In maglev train, that powered by EMS, electromagnets are built into the track. The vehicle bottom is shaped like the letter C, wrapping around the track and hovering above it with the charge of the below-mounted magnet powered by AC. Since there is a 15mm distance between the vehicle and the track, minor change in the distance could cause instability. Therefore, the EMS system need a constant feedback control system, which is the most significant disadvantage. Next, we will go into the part about what reform we can implement to make this maglev train better by using the latest technology application. Firstly, how to effectively brake and guide ultra-high-speed maglev train. This problem is directly related to the safety of the passenger. If the problem of efficient braking and guidance at high speed is solved, the reliability of maglev train can be increased, and the research and development of ultra-high-speed maglev train can also be promoted. The perfection of the connection technology of the carriage for medium and low-speed maglev train, the existing high-speed rail connection technology is fully applicable. But for ultra-high-speed train with a speed of more than 600 km per hour, a safe and reliable connection is essential. To receive large amount of traction, the connection must be able to withstand this traction. Second is to improve the convenience of rescue emergency. Ultra-high-speed maglev train often use vacuum-type pipeline, which have excellent compression performance and strong impact resistance. Although safety is guaranteed during operation, if an accident occurs, how can passenger escape in time through the life-saving tools in the car? This is the problem that must be solved. The research result of the above problem may further enhance the popularity and practicability of maglev train. Number 3. Maglev plus vacuum. Combining maglev with a vacuum tube would mean that the air resistance or drag can be vastly reduced, further improving the train efficiency and therefore speed. Elon Musk's Hyperloop is based on this idea. The Hyperloop will have high-speed capsule that glide through tube with a partial vacuum. They will reach the top speed around 1,200 km per hour, allowing you to travel from Los Angeles to San Francisco or from Johor to Perlis in an incredible 35 minutes only. The Hyperloop is currently being the concept stage, but if it becomes a reality, it will definitely revolutionize land travel. But dreams still go further. The EP3 evacuated tube transport technology combines maglev with a full vacuum tube system. Passenger will be transported in a car-sized capsule up to 6 inch, and airlock at the station will allow for the transfer of the capsule without letting air into the system. For the international travel, speed will go up to 6,500 km per hour, meaning you could go from New York to Beijing in just for 2 hours. The developer of this idea called it a space travel on Earth. And the last one is the virtual coupling. This is known as virtual coupling and involves the two trains communicating information about the changing speed and brake activity so that they can decrease or increase the gap between them to the minimum necessary. With shorter gaps between them, more trains could run safely on the road, increasing overall network capacity. And with this such of innovation, we could introduce trains that are able to adapt to the changing characteristics of the line in order to maintain high speed throughout most of the journey and avoid this annoying stop-start period of travel. So that's one of the idea and initiative that want to be generated to advance the high-speed train industry. So what do you think can help realize this mega project?
For the conclusion, Maglev technology, utilizing the remarkable force of electricity and magnetism, has revolutionized the concept of train travel. By levitating trains above the guideways, it eliminates friction, paving the way for unparalleled speed, efficiency, and environmental sustainability. The real-world implementation of maglev trains, exemplified by the Shanghai maglev train and the ongoing development of the Chuo Shinkansen in Japan, showcases the potential to significantly reduce travel times and revolutionize intercity transportation.
Maglev train revolutionized global transportation with magnetic levitations offering high speed, eco-friendly and self-drivable. This innovation represents a major stride toward a more efficient and sustainable future in transit. Passing on the legacy and building the future.